So y'all got any questions before I begin doing something? Nobody has any questions? If not, I'll just keep milling along. Okay, so let me bring up this and kind of give you an outline. Maybe I can collapse that. So, okay, so the way I'm going to do this, we technically have finished this one. And early in the book, or I don't know if in this edition, but in the previous editions, talk about the way you can cover the material, and most people cover it 12, 13, 14, 15, 16, and 17. But he said a lot of people will do 12 and then 16. So this one they'll do first, and this one they'll do second, and this one they'll do third, and then fourth, and then fifth, and so on. And this is the way I like to do it. And the reason being is because these, it's kind of a lull. These are, I don't consider them a lull, but they're kind of different. This and this one are, this one's a setup for this one. So a lot of times by the time you do this and this and this, you kind of got to go back and review that one to do 16. And so I figure the majority of the stuff that you might use is in this one anyway. So I usually spend, chapter 12 is quite long actually. And then 16 is, in my mind, is perfect setup following 12. Some books are written that way. 12, then they have this one next, and this one, and this one. So that's what I'm going to do. I'm going to go from 12 and then to 16, and then I'll go back to 13, 14, 15, and so on. So, and the reason being is because I can spend a little bit more time in 16 and make sure we get everything. So, let me start MATLAB to cover the white part of the screen. Plus, I might use it anyway. It's kind of strange using it as a place to write on, but it works okay. Okay, so what I'm going to do today is just kind of go through and lay out all the groundwork of 16 and relate it to 12. And so when we started with 12, you actually started with 12 maybe last semester when you did Physics 1. You had this thing where you had a position, and then you had this. In mathematics, they would put a dot over this. And then they would have two dots. They would have two derivatives, which would be two dots. Now somebody, umpteen years ago, decided to rename these. So this is technically a derivative and a double derivative. And this is the position. And what somebody decided is instead of looking at this or looking at this, they decided to come up with a new symbol. And, now this may seem stupid what I'm doing, but I'm laying the groundwork for what happens in this next chapter. And then somebody decided they would call that a new symbol. And this symbol, they call it velocity. And here's a new symbol, and they call it the acceleration. Now, it just so happens that it's the first letter of that, and it's the first letter of this. So that's probably how they ended up deciding that. I don't know. I mean, I wasn't around during that time, but somebody decided that. Now, what happens when you get into this 16? He immediately starts to go into rotating equipment. And so that's the reason, although there was an asterisk on that section in chapter 12, that's the reason I do that one, is if you look, the velocity back there is r dot ur plus r theta dot u theta, and so on and so forth. So they've got this, so this is kind of a, you could put an x and you could put a y, and you could put a position out here to r and theta. And now we're moving into this there. So this is the section that was in chapter 12. Now what happens in this next chapter, okay, and this is really weird. You have to think about what's going to happen in it, and you'll see it as time goes by. We were stuck with this coordinate system. If we were going to do rotating equipment, we were stuck with that. But actually, chapter 16 frees us from that while still using the notation. But what he does is he says, okay, I got this new thing, theta, which is, here, I'll do this, kind of like, this is a simple term for saying, hey, look at the similarities between these two. So you got theta, and it's not a position, but it is kind of position-like. Okay, so it's position-like. It's not really position-like, but it's similar to this. And then somebody says, hey, you know, we might have a time derivative of that. You know, in other words, you're at 30 degrees or something, but it might have a velocity this direction. It might also have an acceleration kind of in that direction. So somebody says, hey, we've got this. Let's create a new symbol. Now this time we don't have a word that we can pull the first letter off of. So we come up with some Greek thing. And it'll be in radians per second. Now this is similar to this in the way it's structured, in that if you look at it, it's just a new position, so to speak. This is position like, it's not truly position. This one is, take a derivative. Now you have a new term. So they, you know, you could say this is a new symbol. And somebody did it again, two derivatives, but two dots, and they said, hey, we got to have a new symbol for this because we really don't like looking at that. That's the only reason I can think they're doing it. They don't like looking at it, so they're going to have this. And this is some new symbol. Now, the problem, I think, that the reason they chose something like this is that it didn't have, you know, this one has physical significance. This one doesn't unless you put it in the context with this. So, you know, theta dot times r is the actual velocity, one of the velocity terms. But if it's not there, it's just not there, and there's no symbol, there's no word for it. So I think that's why this did this way. Now, what happens is a lot of the stuff is similar. So, you know, when you see this new terms, it's actually like this. Now, you can have, let me kind of compare. Now, what we'll go back to is I'll show you actually how this is exactly like what will generate in 16. So what we'll do is we'll eventually write out the velocity, write out the acceleration. We'll go through and compare them apples to oranges and find out they're actually the same thing. But for right now, I'm going to use this space. So what he'll do in the first 1 or 2 or 3 sections of this 16 is he'll start talking about, oh, you had this speed and this was a constant, this and that. And so if you go back to this, he had a special case. And his special case was such that his acceleration was equal to a constant. And so you get this, and then you get, I should have wrote this one above that one, but it's okay. Now, guess what? There's a special case in which, now, I'll write this way, but I should write it like this. Alpha is equal to a constant. So this is the same special case, and believe it or not, you start looking at it, it looks exactly this time. Now, you see this is borrowed from here, so this is borrowed from here. And then the G is just, I should write this should not be a G. This should be acceleration constant. I haven't had my complete dosage of caffeine yet, so. Okay, so this should be the same thing. Alpha t squared, alpha c t squared over 2. So if you compare apples to oranges, you find out they're kind of the same. The equation looks the same, and then you could say omega is equal to omega naught plus alpha, which that's not the start, how you make it alpha constant t. So in fact, kind of like is this one's kind of like that one, and this one is kind of like that one. So in fact, there is no difference between these two. All you do is replace that with the theta, so you can just go place. You can just say replace S with theta, V with omega, and acceleration with alpha. So that's an alpha. And it's the same thing. There's no difference between these two. Now the meaning is different. There is a different meaning. And the meaning here is that you actually get the position, you actually get the velocity, and you actually get the acceleration. Okay, the mathematics is the same, but this is in radians, this is in radians per second, this is in radians per second squared. If you really want the acceleration or the velocity, you have to go through that equation that I just erased. But throughout this section, he will start by replacing this with this, and he'll start using this. Now the next thing he does is this. Okay, does that all make sense? I'll go to the picture of the book in a minute. The next thing he says is, and I'll throw this at you, and it might seem weird, but he says, all of them, but particularly for the moment, we'll look at the omega. The omega is a vector. Now, back here, it's actually a scalar the way it's written, but how is this a vector? How come is that a vector? That is too, but we'll talk about this one. Why is that a vector? And so how can you change this to a vector? Now, this is written as its value, the magnitude of it, but the vector itself comes from this. Let me just, now that I've written this and shown they're similar, I'm going to use this little area to talk about the vector nature of the omega. And I'll try my best to do. So if you have a wheel, now, okay, so I should say something about chapter 16, and the title is, it's rigid kinematics. So in other words, it's an object, some type of engineering object, part of a car, part of an engine, or part of something in which you hope it doesn't break apart, and it's just a rigid body. So here's a rigid wheel spinning like this. Now, here it is, it's spinning with omega, but why is it a vector? Well, it turns out this concept, let's see. So if you take your hand, cross it this way, that's going in the positive Z. If you take your finger, put here, and rotate like he's saying, then the omega, and I'm just going to make up a number, is say 10K radians per second. Now, that direction is associated with this right hand rule. You're putting your finger there, you're figuring out your hand goes like in the direction of the rotation, and you get that. However, if it's spun the other way, you would take your finger, I'd have to stand over here, take your finger, spin it that way, it becomes a negative. And so that's this one. And so that's how they delineate that. By the way, same thing for the alpha too. It's just easier to talk about the omega. So say alpha would be equal minus 2K radians per second squared. So that's all there is to it. It's just your thumb, as you spin it with your right hand, your thumb points in the direction of that. You can have some bizarre stuff. You could have, let's say you did something silly and you decided, here's your spinning axis, right? And you decided that this was going to be X, this was going to be Y, and this was going to be Z. So you cross X with Y, you get Z. You might get something like omega is equal to 3. I'm just making this kind of up now. So you might get 3I plus, 2J. You can have this. So you can have multiple coordinates. And we'll get to that, although most of the time, if you look at the title, and I'll go back and look at the title, it says planar, I think, at a certain point. Okay. Planar kinematics of a rigid body. That's what it says. So planar kinematics, you can have that. But in this text, we're smart enough to realize that we don't want to make our life complicated. Meaning, you might have a disc rotating or a gear rotating. And maybe it's rotating like this. Now, it's in this plane, but that doesn't mean there's not a third dimension. So let's say you had omega is equal to 2 radians per second. So actually, if you were to write that in the vector, take the X, cross the Y, it goes in the positive direction, my hand's rotating that way, it's 2K. So it's moving or rotating in a plane, and this is the outer plane, this is the outer plane component. And this is kind of strange to look at, but that's what, when he talks about planar kinematics of a rigid body means it's like a wheel, gear, something like that. Part of a car, part of a mechanism. And usually, not always, but usually when you're using a mechanism, you end up making it in a plane. Sometimes you can do something different. You can make it rotate around and come out of that plane, and that's okay. And he actually has examples of that, which we'll look at in a second. So that's how the thing is laid out. Let's start going through the sections, and you'll see how the thing is similar to what you've seen before. Hang on. And what you find out is we can go through these sections rather quickly because we recognize that we've seen them before. So I'm going to have to shrink this down. Okay, I hit that. Oh, okay. I'm just going to shrink that part down here. And I'm going to fit it on a page. Oh, wait, go one more. There we go, it's 100%. So he starts with this. He starts with the fact that, and you'll notice he starts with some sort of blue-looking egg. This could be any sort of mechanism, as long as it's not going to break apart and as long as it's rigid. In other words, if it's a water balloon and it's moving around, that's not a rigid body. So that means any point, A and B, remain the same distance from each other at all times during the movement. So maybe this is A and maybe this is B. They can have this rectilinear motion, which is just left to right or right to left, or curvilinear translation where they kind of go up and down but they're not rotating. And then you can have spinning or rotating, and you can have them general plane motion. So in other words, the object, general curvilinear would be it would just do like this, but if it was rotating too, it could do something like that. So this is general plane motion. It has a translational component and a rotational component together. And they actually can be separated in a way, and that's the whole point. And so if you keep going, you'll see examples of it. And this is something you find when you're trying to move a body somewhere or transfer energy from one spot to another, you're going to have some type of weird mechanism like this. This is not that weird, actually. And you can look at what happens in each one of these. So this one is curvilinear translation. If this distance from here to here is the same as here, then this bar just simply does this at all times. It just goes around in circles. This one, it does, it's rotating about a fixed axis. So it's actually just like that. They just rotate. This one just basically goes back and forth. This one has general planar motion. It'll basically do this. So at certain times, like when it sits right here, this one's going down, and this one was going left or right a minute ago. And so and we'll break down how you can some simple ways to find out the information there. It's not. I can't go any further, so I have to go to the next section. So this is going back to that part of the last part of chapter 12, in which we wrote, in this case, RA is equal to, RA plus BA equal RB. I was thinking of writing that first, and then my brain didn't do that. So in fact, this one is what motion. So here, there's a person sitting here at A. This is what they see. He puts a little thing on there called the translating coordinate system, or you could say it's just moving. It's moving with this person A. So the only thing that A would see B doing is rotating around it. So if two of us are on Earth and essentially we're the same distance apart, then all you're going to ever see is somebody rotating. That's all that's going to happen. And so this notation kind of works out. And then in a minute, he goes down. Hang on. Well, he repeats the same thing. Did he repeat the same? Looks like the same thing. Okay, then he gets to the velocity. Oh, he immediately goes to the acceleration, but he didn't write out the equations. That's probably the next section. Okay, so now he's talking about rotating about a fixed axis. This is what I was talking about. We'll come back to this. I'm going to hold it right here. he has a right hand sitting there like that, and so as you rotate around, now I didn't say anything about the d theta, I just said something about the omega. These two are the ones you pay most attention to, but the change in theta is like that, so that would kind of correlate to this. So essentially it's a right hand rule. Tells you the direction of the rotation, or the omega or the alpha. Then you come in, he does the same picture. Oh, he's doing the same picture again. Oh, on the pictures, okay. Well, no, wait a minute. Everything is the same on the same picture. Let's see, wait a minute. Why does he not put the... Okay, so I'll go ahead and put... Let me spin forward, see if he does put him on there. Oh, no, he doesn't yet. How many times does he repeat that same picture? Okay, well, let me say this about this. If you go back to the previous section, and this thing was spinning, and it has a constant r, this will be your velocity. And technically, okay, so let me see if I can logically work this out for you. So this thing spins, right, omega, and it's a vector, so it's going up, so whatever. Well, we saw a minute ago, it was nothing but theta dot, which actually now has a direction. Now, we saw in the previous thing over in chapter 12 that velocity written in polar coordinates looked like this. Now, we've seen velocity at this point, if it is truly spinning that way, and it looks like it is, that's the blue arrow, it looks like we've got the right direction, it's spinning that way, then and it's a rigid body, then this is where it's spinning about. The distance between O and P remains fixed. Therefore, the r dot's gone. So all you get is this, whoops, equals to r theta dot u theta. Well, guess what direction u theta is? U theta is this way, and ur is this way, according to what we had before. Now I want to throw a curveball at you that's going to come maybe in 2 or 3 pages, and that is, if you take this vector, okay, let's look at this. You got a vector to r. It's just a simple vector. Then you have a vector omega. It's a vector like this. You take omega, cross with r, it goes in that direction. So the question is this the same thing as omega cross r? Is that the same? Because if it is, this one is devoid of any, there is no assumed coordinate system here. This one is assuming polar coordinates. And we borrowed from polar coordinates to get here. Now let's go look and see what he says about the V. And he should have a picture that looks like this, but with this writing on it, I hope. I'm not sure. I saw this picture over and over, and I thought, where's the velocity thing to it? So he keeps going. Angular acceleration, but he doesn't put that on there yet. Oh, we do. Okay, so first, this, forgive me because I'm jumping ahead a section. We'll show that later. So what we'll do is we'll stick to this for a moment, and I hope that I've stuck that in your brain, and we'll try to get through this and get to that section. And then Wednesday, today is Monday, right? Wednesday we'll work a bunch of problems. So here's what we were talking about in the previous thing. This looks a lot like V is equal to V naught plus acceleration constant t. Now you're just replacing the omega with the V, and the omega with a V, and the alpha with the A. This one looks very similar. S is equal to S naught plus V naught T, omega naught T, plus 1/2. This time, instead of the alpha, I have acceleration CT. So these are the same with just variable changes. There's nothing new here. And okay, to give you a physical relationship there, if you go in your car and you rev it up, and your tachometer shows, like 1,500 revolutions per minute, then if you want it to break down and find the omega, the value of the omega, it would be 2 pi radians per revolution. So this will cancel that in a minute, equals to 60 seconds. Multiply this out, and I'll give you the omega. Now, if your tachometer shows 1,500 all the time, then this term is going to be 0. But if you're revving up, it's going to be positive or greater than 0. If you're shrinking down, your engine's going down in revolution, it's going to be negative. So that kind of relates. So this relates to rotational equipment, so to speak. Which there's a lot of rotational equipment out there. Matter of fact, I think most how we get our power movement is through some type of rotational equipment. Okay, so here is his motion of point P. Okay, so I was a little ahead. I'm sorry about that, but he's showing the omega. He shows this R. Now he shows a little bit different, but I'm just writing this down and say omega, this vector crossed with that vector, gives you this vector. Now, this vector, most of the time people think of it being sitting right here, and that's true, but you can move it out here. That's okay. And so it's essentially a cross product. Now, does he show that? I hope so. He used to show it. Okay, he may take a little bit longer to show it. Okay, so here he does this. V is equal to omega R. Okay, so omega R, if this is R, and this is now replaced with omega, then that and that are the same thing, i.e. polar coordinates cover all this, but they're stuck in polar coordinates. We're going to unstick us from polar coordinates and move us back to any coordinate system. So the goal here, what the byproduct will be, everything you see of polar coordinates, take the r dot and the r double dot and set them equal to 0. That'll be your acceleration and velocities. You look back over here, you're going to see the same thing on these other terms. So there is no difference, but we will free ourselves of polar coordinates and move into standard coordinates. We can still use polar coordinates if we want to. We can use any coordinates if you want to. Okay, so he says, now he's saying, if you look at this, okay, so I don't know how to shrink it, but he's saying I put a vector from here to here to identify that point P. And then it turns out that he will go through this process using that funny angle right there to show that that's the case right here, which is omega cross R. Now he put a P on it. That's identifying a particular location. So likewise, he should have put a P right here. So if you want to specify a particular location, that has a subscript of P as well. Turns out nobody ever puts, but well, I guess they do put, yeah, so I have to take that back. Accelerations are kind of interesting. So there is a tangential acceleration. Now, if you don't mind, it looks like I have more space over here. V is equal to R dot UR plus R theta dot U theta. Now, I can never truly remember the entire setup here, except unless I derive the thing. Now, I don't know that I want to do that, so I think what I'll do is I'll do this. You should be able to find, I don't know what this is, Proof Wiki. What is a Proof Wiki? Proof Wiki. How about that? Well, that's an interesting, he kept the derivatives in there, but that's fine. That's kind of interesting. I was putting mine first here. So I was putting minus R minus R, and this is theta dot squared, and then you got R, I don't have much room here, R theta double dot plus 2 R dot theta dot. So he has the same base vector, I'll swap those two. So I'll go back to the thing, I've just borrowed that from that guy, I don't want to have to memorize that. When I have to produce it, I'll go back and derive it, and I don't want to waste your time. So, again, if I say R dot equal R double dot equals 0, these two equations will give me this. R theta dot U theta, and the accelerations, that one's gone. This one's not. This is the centrifugal, the same thing as V squared over rho, or R, whichever one you want to do. And then you get this term, plus, that one's gone, this one's not. Now, in our new world, this is what I get. R omega U theta. Now we'll pay attention to this, and then over here I'll get A, accelerations equal to minus R omega squared UR, and again we'll pay attention to that, plus R alpha, because that's what that is. And let's see if this is what he comes up with. First thing he says, the T or tangential is alpha R, or alpha R, same thing. So that is what he's calling tangential, meaning that the disk is spinning, there's an acceleration tangential, and there's one normal. So the next one we got to deal with is this. And you go in here, he just writes it down. He says the normal is omega squared R. R omega squared R. Now, he just says normal. I'll spin this down and we'll look at it. And what you see is, okay, why do I have a minus and he doesn't? Because the normal is going back towards, from the point back towards the center of rotation. And we have to remember, this is my UR, and that's my U theta. So my tangential acceleration, how fast the engine is spinning up faster or decelerating, is this, that one. The spin rate, which this term, believe it or not, is nothing more than that, what you learned before. Just so happened that in all cases here, the R remains fixed. It's rigid, so it's fixed. And so you end up with something like that. Now, is there a more convenient way to write this? And in fact, there is. If you come back to here, I'm going to do this real quick, but maybe I shouldn't, but maybe I should. I don't know. So if you had the velocity of a certain thing like this, and you're in this new realm where your coordinate systems are embedded inside of that, I'm not dedicated to any particular coordinate system, then I can say this, that's supposed to be a T, is equal to cross RP plus, oh, that's supposed to be, sorry, that's supposed to be omega. Now, this one's pretty simple. It's alpha cross RP. This one is actually pretty simple because that is actually that. So it's omega cross R. That's the general vector description where you're not dedicated to any particular coordinate system yet. You've just written it that way. That's the acceleration. It turns out there's your R alpha, your R and your alpha. And this one's weird. But guess what? Omega squared R. Wait a minute. Omega R. So in fact, this is the general form that he's going to write in a minute. And this is specific to polar. So in fact, all of this stuff you've already done. And I don't know how he generates the general form. He does say something interesting, okay? And I sometimes don't like this, but let's look at it like this. If we take that term inside here, and we take omega cross R, that is in this direction. This is omega cross R. Now, I'm going to cross omega with it. So I'm going to take my omega and stick out here. Here's my omega. And guess what? I take the omega, cross it with that new vector, and guess what direction it goes? It goes back in that direction, the exact way that goes. So that's why you have to put the parentheses here. You have to take care of it first, and then cross omega with this after you've done it. Now, what does he do to generalize that? It's kind of interesting because if you go down, he may not do it till the next section. No, okay, here he does it, okay. So he's taking the acceleration, and he's taking the derivative of this, which is this, cross with that, plus omega times that. So we did the same thing. But then, he does do it. Okay, here it is. But then he makes a generalization. And the generalization is true. It's just some people don't like this. A mathematician loves that. A non-mathematician might like the other approach. And the other approach is simply recognizing that whatever direction RP is, hang on, it goes the other direction. In other words, okay, so you have to look at what this is. This is a vector cross R, and we're gonna use all this. So this is omega squared, and that is that. What is omega squared now? It's the magnitude of that. So it turns out that you can prove that this, if you felt like you wanted to, equals to omega cross R. So if you just take, like if this was 2 radians per second, you took it, you squared it with 4, then you made it go in the opposite direction of R. Remember, R goes from the center of rotation out to that point. This is R. We're saying it goes in the opposite direction of R. Take the 2 scalar, 2 times 2, make it go in the minus R direction. Oh gosh, I talked too long. So that lays the groundwork. What we'll do is we'll use this next time. And we'll actually work a couple problems. Several, I hope. But this is generalized in a sense, so okay. I got to cut everything down.